ways to make loss function choices still amenable to optimization, in particular convex optimization using gradient techniques that require the objective to be smooth. So if we want to do robust regression, right, maybe what we want to do is we want to find an objective. We want to define an objective that focuses less on the large errors, right? So one thing that we could do is we could use the absolute error instead of the squared error, right? The point is that in this particular case, if this is, changing from the squared error to just the absolute value of the error, right? If you think about the error as a function, the loss as a function of the residual, right? 0 is the ideal case, right? The absolute error function looks like this, right? So large errors get penalized linearly, whereas the quadratic function looks like this, right? Large errors get penalized quadratically, which means that you really are going to focus on residuals that are large, because those large residuals are going to get really heavily penalized, right? Fine. So what if we use the absolute error? Seems like a reasonable idea. So instead of minimizing the L2 norm, right, we know that there's a correspondence between this and W transpose xi minus y squared, sum over I, right? What if we minimize the L1 norm of the residuals? So what is this L1 norm? Well, if you just take the absolute values and you sum them over all n data points, that's the same thing as the absolute value of the residual summed over all n data points. That's the same thing as the L1 norm of the residual vector, and that's the same thing as the L1 norm of x times w minus y. Okay. Okay. So if we look at the L1 norm of the residuals, it's basically, there's a correspondence between these two, right? Okay, it's saying we're just going to penalize residuals based on linearly rather than quadratically. Okay. So the absolute error is more robust to outliers, basically, right? So the absolute error, as we had before, is what we had before. It's just the absolute error, right? The absolute error of the red fit is over here. The absolute error of the blue fit is here, right? And we will claim, and you will see in homework and various exercises, that the linear model of W that minimizes the L1 norm here will result in, when you have an outlier like this, a fit that is this blue, that corresponds to this blue fit, right? Okay. This is going to minimize because this error does not get squared, basically. Okay. Unfortunately, minimizing the absolute error is harder, and we sort of talked about this a little bit last time, right? We don't have the equivalent of normal equations for minimizing the L1 norm. Among other things, the absolute value is non-differentiable at 0. We talked a little bit about subgradients, right? You can do some sort of subgradient thing, but the other thing that's problematic, it's harder to minimize non-smooth functions and non-smooth functions than smooth functions. That's pretty clear. But in particular, what really is going on, and you can see it here, is that the gradient magnitude here is the same as the gradient magnitude here, is the same as the gradient magnitude here, is the same as the gradient magnitude here. So if you don't have a very carefully chosen step size reduction, you can oscillate badly. Okay, that's kind of what's going on, right? So a way to get around this, one is there are optimization algorithms that address this directly, and you can attempt to minimize this again directly. But what we're going to think about here is ways to actually smooth this loss, because we don't really care about whether it's the L1 loss. What we care about, if we want to make a robust regression model, is that the penalty for large residuals is not quadratic. Okay. So here's what we can do. Here's an idea, right? We can make a differentiable smooth approximation to the absolute value function. And one example of this is the Huber loss. Okay, cool. So what do? Well, we actually make the loss a quadratic function in some range around 0, squared error around 0, minus epsilon to epsilon. Epsilon you can pick whatever you want, doesn't matter. And then away from that, it's just the absolute error. So it tails off linearly. Okay, so note that there's an h here. That's for Huber, right? That's different than the absolute value or squared, right? That's the Huber loss. So once we've described what the function is, right? We have some join points here at epsilon. Then we just have to say what the functional form is such that they marry up. And you could fiddle around with this for a little while at home and get it right without any trouble, right? Basically, h of r is 1/2 ri squared. That's this right here, for the absolute value of the residual less than epsilon. So in this range, the value of the Huber loss is a quadratic loss. And it's asymptotically linear otherwise. But in order to get it to wire up correctly at these epsilon points, you have to set the slope and the intercept appropriately so that it parameterizes by epsilon, right, correctly. Okay, pretty straightforward. H is differentiable, right? Because of this equality sign right here, you can look and see that the gradient at epsilon and minus epsilon is just minus epsilon, right? Is epsilon or minus epsilon depending, right? That's cool. So basically at the inflection points, because of this equality, we have a gradient, right? It's clearly a convex function, right? But unfortunately, if you try to take the gradient and set it equal to 0, this does not give us a linear system like the system of the normal equations that we had before, right? But since we know how to do gradient descent, it's no problem. We can still do gradient descent. And because it's a convex, smooth loss function, we get the nice properties of gradient descent. So cool. Any questions about that? Should be pretty straightforward. But what you should be internalizing is the idea that the kind of model that you arrive at is dependent on the choice of loss, and the choice of loss, even the mathematical form of the loss, makes a big difference. Shauna, yeah, I think it is. I think it's pretty neat too. So we can go. You can imagine you might want to go even further, right? So the squared error is not robust, right? The absolute error is more robust, right? You can imagine other error functions that are non-convex that are even more robust, right? Like this still penalizes linearly as you go far away. If you had something like the square root, this is going to penalize sublinearly. You could even make error functions that say that you get a constant amount of error no matter how far you are away, right? It's just bad to be far away. Right? Such non-convex errors are much more robust. They're non-convex because we can draw a line here, and these things are not above the function, right? And if you fit regression, you can use them for regression, right? The issue though is that well, you can fit them, and they're not going to be influenced even by outlier groups, right? So an L1 error on a data set that looks like this might give you a regression relationship that looks like this, but super robust errors might pick this line, but because the objective is non-convex, you're going to have a hard time, or you might find local minima rather than global minima, and you might actually end up with this regression relationship rather than this regression relationship, and you might need multiple restarts and all that sort of stuff. What exactly does robust mean in this context? Are you saying so the only notion of robustness that we're using is that residuals that are far away from 0 are not heavily penalized, right? So the point is that in order for there to be, let me flip back and just look at this data set. In order for there to be a fit of this data set, right, what's going to happen, right? You can either fit this line, that's one option that you might want to have, and then you're going to have all of these residuals, or you can fit this line and you're going to have all of these residuals, right? So one of them is, it's in the eye of the beholder which one is the one which one that you want, but you would, I guess, rather have a fit that actually corresponds to one or the other. The point though is that really the meta point is that the loss function that you choose influences the model and the generalization performance of that model rather dramatically. That's really what we're trying to communicate here. That's the meta point. Okay. And in fact, you might not want robust regression, right? So let's say you're, predicting tornadoes from some sort of data set, right? Like it's not a really good idea. It's bad if your app misses a tornado. You really want to be sure, right? So what if you really care about getting the outliers right? What if you don't want your O-ring to fail and have your rocket explode, right? Maybe you want the best performance on the worst training example, right? What throttle inputs should the autopilot supply if you get a very, if the observed relationship on which you're training says to do something extremely different than all the other data would lead you to do. Right? So what you could do is you could do something like the infinity norm, right? And this is one of the more beautiful parts of the course in terms of like what it introduces and how it gets you to think about it. So if we make the loss function for our regressor the infinity norm, this basically says that the infinity norm of the residuals says we're looking for the max over all of the individual absolute values of the residuals, okay? And we can think about what a regression relationship like this is going to do, right? So it's going to take the biggest loss and try to make it small. And then it's going to, whenever that gets small, it's going to look at the next biggest loss and try to make it small. And it will keep doing this until basically all of the losses are about the same, regardless of how many of these there are, right? So in this particular case, this data point is going to pull the entire regression relationship closer such that you have reasonable performance on this, what would be an outlier, but maybe is actually a really important point. Okay. So brittle regression or infinity norm regression is very sensitive to outliers, but in the worst case situations, it can be better. And this is really one of the prettiest parts of the course right here. So as with the L1 norm, the infinity norm is convex but non-smooth. You've got the max in there and absolute values and all sorts of stuff, right? So we can again use a smooth approximation to it and fit it with gradient descent, right? And this is really such a beautiful way to introduce this, right? So a convex and smooth approximation to the max function is the log-sum-exp function. Okay? So let's look at this. Okay, think about what's going on, right? So here we have some arbitrary vector values z, zi to zn, z10, z1 to z10, whatever, doesn't really matter. And we want the maximum element of that vector, of that set of numbers. Right? Well, if you look at what's going on here, and we'll explain this in just a little bit more detail, what this says is that in value, the value is going to be close to exponentiating all of the individual elements, summing them up, right? And then taking the log. And now what's going to happen, if you think about it for a second, is that the largest number in that set is going to be exponentially magnified, and all the rest of them are going to be like little decimal points, right? Even for very small differences between the values, right? And then when you take the log of the sum, you're basically going to get the maximum value back, okay? And we use this a lot, actually, in the course, okay? So it's worth really getting an understanding of this, right? And as I've said before, when I write log, I mean natural log, and it doesn't really matter if it's natural log or regular log. Doesn't really matter, right? But just know that when I write log, I mean natural log, because if I write natural log, half the time it looks like an H or some horrible other scribble. So if I write log, it's a little bit clearer. Okay. So the intuition, as I already gave you, is that basically the sum over all the elements of the exponentiated value of the elements is very close to the maximum over all of the exponentiated.
Computationally more efficient than just going over the vector and finding the max?
Okay, good question, Akeem. So in a single vector case, maybe not, right? But we will see a fairly large number of examples in the near term where we want to search in a combinatorial space where it would be more or less impossible to just search for the individual element, right? Because we're going to be in some combinatorial space where we're simultaneously finding the max of a large number of sets. Good question. And again, the point here, yeah, of course, notice if you take the log of x of z, it's just z, right? So the point here is to build a smooth approximation to max, okay? So just to do some numerical examples, if we have zi is this, well, the zi is an element in this set, right? Okay, Payman, what's the maximum of this set, and what's your guess as to what the value of log-sum-exp of all of the elements of this set will be?
Max is 20, right?
Yeah.
Well, I guess it's going to be close to 20, something like that.
Yeah. So the max over the set is 20, and in fact, actually, the numerical value for the maximum for log-sum-exp zi is 20.00002. Okay. Interesting, right? Okay. What if we put 19.99 there? What's the max of that set? And what do we think the log-sum-x value is going to be? Yeah, exactly.
Yeah.
The exponential function is a weird function, right? It's very important, right? So 20 is still the max, and log-sum-exp is 20.6 something, right? Okay. So this is a pretty good approximation, right? So if we just have two values, you know, or rather, if we look at this, if we look at max as a function, if we look at max 0w as a function of w, right? This is what it looks like, right? And we look at log-sum-exp as a function of w, right? This is what it looks like. Okay, so it's an over approximation to the same function, right? And you'll notice that these get very, very, very close, right? Okay, cool. Awesome. We've made it somewhere again. Yay! Awesome. Good job, you all. We're keeping pace, even through COVID times, online lectures, horrible Vancouver weather, the imminence of fall, you know, bad professor, changing hairstyles, all this stuff, right? Okay, so we're done with part 3. Awesome. Yeah, Vancouver weather is great. Yeah, right. Not this time of year. So the key idea is in part 3 are linear models and least squares, right? The focus of part 3 was linear models. And it's basically supervised learning where the prediction is a linear combination of features, right? So we have our features X, our d-dimensional features, and then a weight vector. Those are the parameters for our prediction program, right? We need to learn those. Right? And what we've been talking about is regression, right? Where the target yi is numerical, and testing exact equality doesn't make sense. So what we're after is a good fit that doesn't exactly hit all the data points, right? That's okay. And we started talking about squared error, either in terms of individual data items or in terms of the squared norm of the residual vector. And we derived the normal equations so that we can solve them in the least squares case for an optimal parameter, right? We introduced a very powerful concept that's going to stick with us through the rest of the term, which is basically a change of basis, where we replace the features X with the nonlinear transforms Z. We started with adding a bias variable, which allows the regression to not pass through, the regression relationship to not pass through the origin at feature value 0. Then we started talking about a polynomial basis, right? And we showed that this makes the regression relationship much more flexible at the cost of potentially overfitting. And then we talked about feature engineering, where you can add all kinds of basis functions to your new basis set Z that might be inspired by the problem or so on and so forth. Basically, it makes the nonlinear regressor more powerful and more application specific, right? And inspired by this, we started to get you to think about the fact that you might want to, as we will do throughout the course, we'll get you to think about increasing the feature set and then ways to decrease the feature set and increase the feature set and decrease the feature set, leading to overfitting and generalization and overfitting generalization. But now we're in the phase of, can we make D really big, right? And if we do, then this is one of the motivations for gradient descent, even with the complete data, where the iterations only cost order n times d. We know that gradient descent converges to a critical point of a smooth function, regardless of whether or not it's convex. But for convex functions, it will also find a global optimum. Right? And then today, we talked about error functions and smoothing, right? Where we've been talking about the squared error all along, and that's part of our model. But now we know about the absolute or L1 error and its Huber error approximation, which makes the regressor more robust to outliers, and a brittle error is more sensitive. The L infinity norm is more sensitive to outliers. L1 and L infinity by themselves are convex but non-differentiable, and like trying to learn model parameters by minimizing those errors directly is harder than just doing than learning the model parameters under the squared error. But we can approximate these with differentiable functions, Huber and Log-sum-exp. Okay, and this one in particular, you really want to jam it into your head. It's an important one. And with these smooth convex approximations, we can find the global optimum with gradient descent and a minimizer. Okay, cool.
What's residual?
Residual is indeed and I have used it several times because it's Ri is W transpose Xi minus Yi. Right. Or
is that the same as the error?
It's the error. The residual is the error on an individual data item. Yeah. And it doesn't matter. The sign, whichever direction you make it. This is always either absolute valued or squared or something like that. So the direction doesn't matter. Cool. The good news is that as of right now, you've made it to the end of the midterm material, right? So we're not done with part 3 entirely, but basically after this, you're not gonna need to learn to an absolute level of mastery the stuff in order to do the midterm, right? Of course, the midterm, just to be clear again, is going to be much more practical because it's take home and so on and so forth. But still, the stuff that you'll need to actually do the take home midterm, basically you've got it all now. So once you internalize it, you're good. You're ready to go. Okay. Cool. Any other questions? Good point for questions. When's the midterm? Check the course calendar on the course website. It's a couple weeks from now. It's going to be fun. You'll enjoy it. Early indications are that you will be doing some Biden versus Trump Twitter classification. It'll be fun.
The midterms can be in groups, right?
We'll get to that. So robust regression focuses on larger outliers. No, Kevin, that's exactly the opposite. Robust regression ignores larger outliers. Right? And yes, you will be using LaTeX for your midterm. Yeah. Cool. All right. I can see everyone is excited for the midterm, as excited as I am. That's great. What's the time limit on it? Oh my goodness. It's all in the, 1 week, I think. It's not all on the course website. It's pre-planned. You've had all this information since the day one of the course. And what am I going to get? Nothing but grief. No positive reviews. It's all grief. Okay, great. Let's finish up with thinking about what it would mean to find the true model. What if our goal is to find the true model? What if we, lived in space, didn't need to breathe, we're discovering the law of gravitation, no friction, blah, 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 blah. We drop a bunch of stuff, we see how far it is away. There is actually some true model there, right? There's, the laws of nature, right? Newtonian laws of nature, right? So what if our goal is to find such a true model? Right? In our class, we're going to believe that our output is actually really a polynomial function of our input, x, right? And what we want to do is find the degree of the polynomial, right? So, Damon, should we choose the p with the lowest training error?
No, not really.
Nah, exactly. Why? That's the question. Why? Because it's going to pick a p that's always too large, right? Because you can always decrease the training error as you increase p. So should we choose the p with the lowest validation error?
That makes more sense, I guess. But well, that also will result in large p, right?
It can, and that's the point. So again, validation for the error for the win, maybe. We have to be very careful because there's going to be measurement noise, right? Right. And this will actually often, not super often, but it may choose a p that is too large, right? In particular, we know that the true model, right, is, if we know the true model is a second order polynomial, we know that that's a special case of a third order polynomial. We know that's a special case of a fourth order polynomial. We know that's a special case of a fifth order polynomial, so on and so forth, right? We know that we overfit when p is too big, but we might also just get lucky and get a lower validation error. This is another example of what we talked about in terms of optimization bias. I mean, but it's not bad to choose by validation error, but you do need to be careful that these are sort of like nested these models are nested amongst themselves, right?
Can we use bootstrapping to build multiple cross validation data sets?
Oh yes, we can do all sorts of stuff. Good idea, Shanik. That's great. But no, let's just cut right to the like right to the heart of the matter and say that what we want to do is we want to actually impose some sort of model complexity penalty. And again, here the specifics are not so important, but what you should really be internalizing and taking away from this is that a good thing to think about is that we may actually want to explicitly penalize model complexity. And this is going to end up, you can sort of, to foreshadow, we've been saying, okay, let's add features, let's add more features, let's make really big features, right? That's a good idea, it makes the model really powerful, but somehow we'd like to also simultaneously push the model complexity down, like prefer simpler models, apply Occam's razor, so to speak, right? So there are lots of scores that people use to find the true model to penalize model complexity. And the basic idea is that they put a penalty directly on the model complexity. So, and it's the Occam's razor idea incompletely. You want to fit the data and have a simple model. So, for example, you might minimize the training error plus the degree of the polynomial. So here's our basis Z, right? And let's find a P that minimizes the following score, right? So note that this Z is parameterized by P, and P here is the model complexity. Yeah. And Ramon, your comment about compression is spot on. One interpretation of this is the number of bits to transmit the model before you transmit the data. Okay. So this term is the training error.
Data values are very large.
I have no idea what that means. So this is the training error for the best model parameter V in the basis ZP with this particular basis, and P is the degree of the polynomial, right? So if we use P equals 4, then the score P is the training error plus 4, that's our error, right? And if two P values have similar error, we prefer the one with the smaller P. So how do we optimize this score? Pretty straightforward, right? To form Z naught, we form Z naught, solve for V, compute score 0, so on and so forth for all the different polynomial orders, and then you choose the degree with the lowest score, right? So basically it means that you need to decrease the training error by at least 1 to increase the degree by 1. Okay, fine, cool. And there are lots of forms of this. There are many, many different kinds of scores, and they usually come in the form of loss plus regularization term / penalty, whatever. So the value K here is the number of estimated parameters or degrees of freedom in the model. For the polynomial basis, we have K equals P plus 1 because there's the 0th order term. And this term lambda controls how strongly we penalize complexity. In other words, basically, how much you need to decrease the training error by at least lambda to increase K by 1, to increase the polynomial order or number of degrees of freedom in the model by 1. If you use lambda equals 1, this is called the Akaike information criteria, AIC, and there are other choices of lambda that give other criteria, okay? So how do we optimize this score in terms of P? Same thing, oops, sorry. You form all the bases, right? You compute the score, and you choose the best performing score, right? So we need to improve by at least lambda in order to justify an increase in the complexity or expressivity of the model, right? In other words, if we make lambda big, we'll choose a lower order polynomial model. If we make lambda small, then we'll choose a large degree polynomial. And to answer Dominic's question, like, isn't this exactly what we did with depths of trees earlier? Yes, more or less, actually. Yeah, it is directly a measure of model complexity. The depth of trees is not exactly this K term here, because the depth of tree increases the model complexity by a large amount. It increases it by all the parameters at the next depth. So those models have a larger they have a larger number of degrees of freedom as you increase the depth. Anywho, today, in summary, outliers in our outputs can cause problems for least squares. If you use an L1 norm, this results in a robust regression that is less sensitive to outliers. If you use an L infinity norm, that's a brittle regression that's more sensitive to outliers. And if you want to train with models with these particular losses, resulting in robust and brittle regression respectively, then we need to impose smooth approximations that basically accomplish the same thing, and it allows us to run gradient descent even with non-smooth functions. So the Huber loss approximates the absolute value, and log-sum-exp is a smooth approximation to the maximum. And we talked about at the end here information criteria that are scores that explicitly penalize models based on their number of parameters, right? And this is useful when we want to think about learning or finding the true model. Okay, perfectly timed again. Thank you very much. Are there questions? I think this is do we just need 4? No, you should, continue until whatever value of lambda you use, this score increases. You just go down, 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 down. The first time it increases, you know that it's going to increase from there. So you just need to go until it increases. Why would we want to have a less complex model apart from concerns of overfitting? Well, I would say that the concerns of overfitting and lack of generalization are pretty extreme. That's what's going to drive most of these kinds of model complexity considerations, because generalization performance is what we really want. But a less complex model also is computationally less burdensome usually. Okay, so why do we need to approximate max by log-sum-exp? Okay, so let's imagine how you would fit a brittle regression model with the maximum, with the L infinity norm, right? So what you would do is you would identify the maximum and then adjust the weight for that maximum until it's no longer the maximum. Then you'd find another maximum. Then that would result in another one with maximum error, and you would adjust that weight for that, and so on and so forth. Like it's not clear how to even write down an algorithm that would provably converge if you're actually switching between the dimensions of a very, very large data set and focusing only on one dimension at a time, right? Because some other error is going to pop up, and another error is going to pop up, and so on and so forth, right? So it's possible that would be that you could do a stepwise optimization procedure like this and have it actually converge, but maybe not. It's hard to say. There's a lot of stuff going on here. Okay. If we have a lot of noise, whoa, how do we, whoa. If you have a lot of noise, lambda k. If you have a lot of noise with a lambda k value, have less weight. I mean, you can see what we're writing down as the score here directly, right? So if these are very, very large terms, then this is not going to matter as much. That's correct. Yeah. So this is why we overfit with the validation error. It's really about the fact that, like, even with the validation error, if you have data that's like this, I should put a little more clearly. you have data that's like this, and it's almost perfectly quadratic, right? So you're going to fit a quadratic to that, but actually your validation set is just slightly, that has a slight, cubic component to it. Like you're just going to overfit to the validation error just ever so slightly, right? And the difference between the quadratic and the cubic is, and the quartic are very, very small. I don't know where that went. So it's possible that you could choose one of the infinite, basically, number of polynomials that match the quadratic in that spot, just because of slight variance in the validation set. Okay. If you have 8 data points, a degree 7 polynomial will fit perfectly. Correct. How do you define the true model? Yeah. Let me just do a really dumb example, okay? This is actually a fun thing that I've done for children, right? That want to understand let's see. There's a bunch of ways we can do this, right? We can plot a bunch of circles of varying radius and circumference. Both of these things can be measured approximately, right? But there is a true model that relates the radius and circumference. So if you didn't actually know this and you somehow knew linear regression, but you didn't know geometry, you could go off and you can measure this and you can measure this for a bunch of different values of radius and circumference and fit a regression model. What should the true model be, Lily? There are some circumstances in which there is a true model, right? Akeem, oh my goodness, if we minimize for 3 and 4 and we find the training validation error is the same for both and we take k equals 5, do we pick 3 or 4? That's a philosophical question. Occam's razor would say pick k equals 3 because it's a simpler model, right? Always take the simplest explanation if you can. That seems to be a pretty reasonable, yeah. Declan, is this kind of optimization with respect to complexity compatible with cross-validation? Is the score using training error or validation error? The truth is either or both. You can do this with validation error or with training error. I prefer to think of this with training error. Cool. Any other questions? If you use training error, is there a point to cross-validate? Yes. It depends on whether you treat it as a hyperparameter or a parameter. That's really it. Is there a way to increase the weight of the lambda k parameter? Yes, increase the value of lambda. I think that does it. Thank you all. Enjoy the weekend and happy Thanksgiving.